Hey folks! Today we're going to talk about Steno's laws and unconformities. Prompts to screencast, and here it is. Let's get started. So first we're going to talk about Steno's laws. There are a few of them. First is original horizontality, and then superposition, lateral continuity, faunal succession, and then cross-cutting relationships, which tie everything together. Next, we have unconformities. These are the answers to questions that geologists ask in the field. So we have disconformity, nonconformity, angular unconformity, and then we'll briefly talk about paraconformities. So we'll start with the law of original horizontality. Basically, it states that strata, or layers of deposition that turn eventually into sedimentary rock, are deposited flat. They can eventually be folded, but they are originally deposited flat. This is a great representation of that. You can see that there's a valley that was eroded maybe by a river, but then it was filled in, and it was filled in by flat layers. That's the law of original horizontality. And that's the first law, and it's very important because it helps us understand the timing, the relative timing, when we're trying to figure out in the field and we're looking at an outcrop or a rock face, and we're thinking, what came first? Well, we know that things had to be flat to begin with, so if we see a fold, that gets us thinking. So the law of original horizontality is very important. Next is the law of superposition. You can see on the left there's numbers, but the numbers start at the bottom. That's because the bottom layer is deposited first. In that valley, you know that the bottom layer was, say, deposited by a river. And then there's a layer on top of that, and then a layer on top of that. Superposition. Position, where it's located, and then super, meaning above and above and above. Whenever I look at a cross-section, I always think of it from the bottom up. And I do that because I think of the timing of deposition, the timing of formation, and it's usually because of superposition. The bottom is older than the top. Alrighty. The law of lateral continuity. This is a great figure. It shows that we can have no data, but still know that there was something happening, right? So we can look at the cliff face on the left side and look at the strata, the column, the layers, and then we can look at the right, and they're the same layers. So therefore we can conclude that there was a continuous structure at one point. However it happened, however the mechanism was separated, we don't know. Maybe there will be research to figure that out, right? It could be whoever, wherever on the planet, but the law states that if the strata is the same, even if there is space between it, if the strata is the same, they were once connected. The law of lateral continuity. Doesn't matter how much space, but they were once connected. So the law of faunal succession takes that one step further. It takes those layers and it says, well, were there any fossils in those layers? Because that creates an even stronger correlation. So you can take these columns, and we call them stratigraphic columns. Strata, the layers, graphic, we are graphically showing something, a figure, and columns, because like I said before, when you're looking at a cross-section, like a 3D cross-section of the Earth, I like to think of things from the bottom up. This is the same idea. A column of superposition, so layers from the bottom up, showing original horizontality. Most of these lines are relatively flat. We have faunal succession, showing faunal, meaning creatures, of fossils. And the layers can be laterally continuous across miles away, across oceans, across the Atlantic Ocean. And as we talked about before, there's seafloor spreading via plate tectonics, right? There's a divergent plate margin in the Atlantic Ocean. So there are fossils in South America and Africa that are similar, in Ireland and Nova Scotia that are similar. And the law of faunal succession, as well as lateral continuity, superposition, and original horizontality, all work together to tell us that, to help us understand that plate tectonics and seafloor spreading were the mechanisms that separated Ireland and Nova Scotia, or South America and Africa. They're the laws that connect the dots for us as geologists. So the next thing is the law of cross-cutting relationships. This ties all of those laws we just talked about together. First, we will talk about original horizontality, right? So we know C, layer C there at the bottom, the very bottom, the blue, that had to be deposited first. So that's number one. C was deposited first. And then B, because that's on top, so we know superposition. And then B, because of superposition, right? So C, B, and A, that's the first three that were deposited. And then we have an intrusive dike, letter D. So we have these layers, and then we have a dike that intruded through it. That relationship of the dike intruding through those layers is called a cross-cutting relationship. So we know, relative timing-wise, that D is younger. D is younger than the layers that were there before it. It has to be. The layers had to have been there in order for the dike to cross through it, right? So it's like a puzzle. We're constantly trying to figure out a puzzle. So C, B, A, and then D. And then, all of a sudden, we have a fault, letter E. The fault comes in and cross-cuts the dike, letter D. So we have two cross-cutting relationships here. We have the dike cross-cutting the sedimentary layers, and then we have the fault cross-cutting the dike and the rest of the layers too. So cross-cutting relationships, though, they allow us to, as geologists, to tell the bigger story, because in the field, in real life, we're not going to see perfect, pretty pictures like the rest of the laws that we've gone through so far. We're going to see this. In reality, this is the type of thing we're going to see. And even this is a very simplified version. Mother Nature didn't make very many of those simple valley horizontal bedding with no folding relationships. That's not most of the world, right? We have to be able to think critically and problem solve and solve puzzles. Okay, now we're going to talk about unconformities. So unconformities happen when there is some type of gap in the geologic record. So these dark lines represent that gap. It can happen due to erosion or some other process, and it's a question that we ask as geologists because it's something we see in the field or we don't understand. So the law of superposition tells us that the bottom is the oldest and things should be, and then original horizontality tells us that everything should be deposited flat. So like the top left-hand corner there, the disconformity shows that there's flat layers, and then all of a sudden there was some erosion that happened and then more layers were deposited. So we'll go into each of these types of unconformities, but essentially an unconformity is a gap in geologic time that is recorded, or that is not recorded, or essentially kind of is recorded by the gap. You know, we can't see data, but we see that there is a gap of data. It's represented by this dark line because we can see that something happened, but we just don't know what it is yet until we do more research. All right, we'll talk about disconformity first. Take my photo out here. Okay, so that's essentially what I was just speaking about. The layers have the same orientation, they're horizontal, and a layer has essentially been removed due to erosion. Happens over time. So there was water, there was deposition happening, say due to the sand and the beach and the waves. The water receded, and now erosion is happening because there's rain and stuff is being pushed into the ocean. Well, guess what? Sea level rose again. And now deposition is happening again. Well, that point of erosion in the middle, there was a gap. Everything that was once there, all that sand, is no longer in the geologic record. So that is essentially that black line. And that's an unconformity. In this case, it's called a disconformity. It's a type of unconformity. And it happens over time. That's the point, is they happen over time. A nonconformity is when sediments are deposited on top of an eroded surface of igneous or metamorphic rocks. So the last example was on top of sedimentary rocks, right? It was a beach environment. It can happen in that valley of the original horizontality video. Sedimentary basins, basically. Nonconformities happen with igneous or metamorphic rocks. Now remember our discussion on chemical weathering. These rocks are much more difficult to weather. So the fact that they're relatively flat and horizontal, that shows that there's a lot of time that has gone by, right? A lot of time, it takes a lot of time to erode more igneous and metamorphic rocks. And we learned that due to the chemical weathering processes in previous chapters. So nonconformities happen when there is batholiths or igneous formations under the surface, and then say sedimentary rocks fill in, like in that top number 1. Erosion happens over time, flattens it all out. Sediments come up on top of it, horizontal, as we know, because of original horizontality. But we have this nonconformity. How do we know what number 1 in this figure looked like originally? As geologists, how do we figure out that there once were these funky shapes under the surface? How do we figure this out? Well, we have to make assumptions and correlations. We have to look at the type of rock. We have to look at the types of rocks of the igneous formations. And then we also have to look at the more sedimentary rocks that were deposited on top of it. And we have to look at the whole setting to figure this out. The tectonic setting, how are the igneous rocks intruded up to the surface, and then how are the sedimentary rocks deposited? It's an entire process. It's not just looking at a cross section and saying, oh, that's the answer. In some of these you can, but when you have these nonconformities, it's a lot, and just unconformities in general, it's a lot more difficult to figure out what happened in the past. But by identifying that unconformities exist, geologists were able to draw more conclusions. It was a great tool. So angular unconformities are one of the last, or are pretty much the last unconformity that we will focus on. So it's when new strata or layers are deposited on top of tilted and eroded layers. So the main point in here is that that bottom layer is no longer horizontal. It's now angular. It has been somehow folded tectonically, and then deposition has occurred on top of it. So say there was a mountain building event, which we call an orogeny in geology. So a mountain building event, so an orogeny happened. Say the Appalachian Mountains. The Appalachian Mountains formed. All these mountains, now they're starting to erode. Well, now there's deposition happening on top of it. On the very, very old mountains that are, say, in on the outskirts of the Appalachians. Because the Appalachians are very old mountains. They're not like the Himalayas, although they once were almost as tall as the Himalayas. They have eroded down, right? So strata can be deposited flat on top of past orogenies, is my point. And that is called an angular unconformity. And it helps us understand what has happened in the past. And this is probably the most common unconformity, I would say, because this is realistic. This is what we see in the field. Tectonics happens, right? We know this. Realistically, we're going to see a lot of folding in the field. So we have to be prepared to figure out the story behind it. And then briefly, we'll just talk about paraconformities. Paraconformities are sedimentary rocks with parallel bedding, and then suddenly there's like a missing parallel bedding. And bedding is essentially just like the layers, right? And we're missing a layer. We don't know why. It's like this thing we don't know about. Geologists need a word for it. We still don't know why. It's like this enigma. It's difficult to see the gaps in time. There's not a lot of signs of erosion. And it's really just a word we use when we don't know what it is. And you'll see it in almost all of the figures on unconformities. And it's really just something that is included for people to just, it's like the garbage can word. I don't want to say that in an insulting way, but that's essentially what it is. And this is just that last figure real quick. So then I wanted to show you, I'll take my face back here. All right. The Lions Formation in Colorado. This is an awesome figure that shows the strata, right? We have our stratigraphic column in a way that is expressed in time on the right. And we'll go through geologic time in just a second. But then we also have all of these layers. You can see the horizontal layers. You can see angular nonconformities, disconformities, angular unconformities. I'll post this on Blackboard if you want to take a closer look at it. Okay, finally we're going to talk about the geologic time scale. The Geological Society of America puts out this geologic timescale, and it is the gold standard. I personally use it quite often. It's referred to all the time, and they update it quite frequently. The way to understand it is we start at the bottom right-hand corner. That is the oldest. It's the Hadean time and the Archean. We move upward to the Proterozoic, and that is all the Precambrian time. That is the oldest. And then we move into the Paleozoic, and we start at the bottom of that column, and we move up. And then the Mesozoic and the Triassic, and we move forward. And then upward. And then the Cenozoic, and we start at the Paleocene and move upward. So we start at the bottom right, at the bottom of the column, and move upward. That's how we read these time scales. And it's important to note that it's a logarithmic scale, too. So sometimes it's not always, 10, 20, 30, 40, 50 for your times. You have to look at the age in the left-hand column there to make sure that you're reading your ages correctly. And then you'll also see magnetic polarity in those younger ages. So we can use magnetic anomaly readings from rocks and continents and movements and tectonics and lots of different where things were moving, essentially, around the planet, and how individual mineral grains were oriented when they cooled. So they're essentially like little needles on a compass. And if they're pointed north, they were magnetic. We know when they cooled that they were pointed north, right? If you have a little hematite iron crystal, oh, it's pointing north. And you have a bunch of them in a magma chamber. Okay, well, it cools, and then you move to another location a few kilometers away, 100 kilometers away, you have the same situation. Well, 100 million years go by, tectonics change, that whole Pluton underground is in an entirely different location, but it's already cooled. And those little needles are no longer pointing north because it had already cooled, and tectonics have changed the orientation, right? So they use these magnetic anomalies, the polarities, they use magnetism to help determine the geologic timescale. Alrighty. And then this is the classic, I will move my face out of the way, the classic photo we see in intro geology. You stick your arm out and you see the little red dot on the tip of your finger. That is where humans exist. And your arm is the rest of life. Not even the rest of Earth history, the rest of life. Life existence on Earth. Now, I know that this can be just mind-blowing and existentially just conceptually hard to understand. I personally do not allow myself to really go super deep into understanding geologic history because I know I'll never be able to conceptually understand it as a human being. I don't try to memorize the dates and times, and I will not ask you guys to do that. I don't think there's a point in it, to be honest. I think we can always access the geologic timescale. We have references, we have the internet, and it's also changing because of data that we are collecting as researchers. And while the general terms aren't going to change and the general dates aren't going to change, I don't see the point in memorizing. However, the general terms like Precambrian is the oldest, right? We need to know that. The Proterozoic, that is when life erupted, right? Single-cell organisms erupted. And then Phanerozoic. Phanerozoic is when we got beyond single-cell organisms. And then we can see in this scale here with your hand how evolution just literally erupted in the Cambrian time. So we have Precambrian and then Cambrian. Precambrian before life, Cambrian after life. And it's really, those terms were created or came up with, and then more research has obviously been done since then. And so exact ages, exact times, millions of years, 100 million years, the exact dates aren't pinpointed exactly anymore. It's not exactly the Cambrian anymore. It's not exactly this date or exactly that date, but it's generally speaking, Precambrian and then Cambrian. For Precambrian before more than single-celled life, So it's pretty interesting. This is the classic intro geology, understanding time in geology, geologic time. photo.